In this video, I'm going to go over exercise 5.1.3 from the textbook. And actually, this is going to be kind of an extensive exercise. So what I'm going to do is actually call this one part 1. Because I'm sure the exercise is going to be so long that I'm going to have to break it up into a series of videos. But before I actually state what the exercise is, if you remember what we went over in class, talking about the time evolution of the wave packet, and we picked a particular initial condition where the initial wave function at time t equals 0 was this Gaussian. And so it had the form, the wave function, so psi at x at time equals 0, had one part which was e to the I momentum initial p0 times x prime divided by h bar times this other exponential e to the minus x squared, I'm sorry, x prime squared divided by 2 times the width delta squared, and that whole thing was divided by pi delta squared to the 1/4 power. And then we evolved it in time by coming up with a propagator, in this case u of x and t starting at a position x prime, which we said was the product of x, the u propagator, x prime ket. So we're starting with the initial position x prime, we're transforming it with the propagator, coming to some other final position x, and when we worked that out, what we got was an equation of the square root of m over 2 pi h bar t times e to the I m x minus x prime divided by 2 h bar t. So then we put that all together and we found the wave function at some later time and position. So wave function psi as a function of position x and time t was the integral of u, basically this matrix element, u x t x prime times the initial wave function x at a time equals 0, and then integrated over x prime, like so. So what exercise 5.1.3, if I pull it up here, what it's saying is, why don't we try a different approach? Why don't we now try and use a different propagator, one that's based on the Hamiltonian, and then we'll take that and expand it with a Taylor series and then apply it to the initial wave function. And the one thing they do to simplify things is to start with this initial condition of the initial momentum is 0 and the width of the wave packet is 1 at a time of t equals 0. And so we get this initial wave function, a simplified version of the wave function for the initial wave function. Okay, so let me basically rewrite that. So the Oh, okay. So we're going to use the initial condition that the initial momentum is 0 and that the width is equal to 1. And so if we apply that to our initial wave function right here, sorry, if we in our initial wave function right here, then that simplifies to psi of x at time 0 is equal to e to the minus x squared over 2 divided by pi to the 1/4 power. So a much simpler wave function. And so what we want to do is now to apply another propagator. And this propagator, u of t, will be e to the minus I, the Hamiltonian operator, times t divided by h bar. Where now, this is still the free particle Hamiltonian. So the original Hamiltonian would be the kinetic energy plus the potential energy, but since the potential energy is equal to 0, it's a free particle. Then the Hamiltonian is just the kinetic energy, and in operator form, that's momentum squared over 2m, and in the position basis, then that is minus I h bar derivative with respect to x squared divided by 2m. So the Hamiltonian becomes minus, because we have the I squared, h bar squared over 2m, the second order derivative with respect to space. So now our propagator becomes u of t, which is e to the minus I h bar squared over 2m, second derivative, times the t divided by h bar. So that simplifies to e to the minus I h t over 2m, second order derivative with respect to space. Okay. And now what we want to do is the way that we use the way that we operate with operators that are inside exponentials is to break them up with the Taylor expansion. So therefore, we have the sum of terms 1 over n factorial I h bar t over 2m to the power n, and then the derivative taken to the n power. So the derivative, the 2nth power derivative. Okay. Now we can also take our wave function, our initial wave function, which is psi of x of 0, which I said was when the condition that there's no momentum and delta is equal to 1, then that is e to the minus x squared over 2 divided by pi to the 1/4 power. So this one we can also break up into a Taylor series. So we have 1 over pi to the 1/4 power, the sum of n equals 0 to infinity, minus 1 to the n power over n, I'm sorry, n factorial 2 to the power n, and then this is x to the 2 n. Okay, so, and this is where the problem says, now that we have these two Taylor series, what you can do is you could expand them. So what we could do is we could expand the propagator into terms. So I have the terms 1 plus I h bar t over okay. So that's over 2m times the second order derivative with respect to the space, and then the next order term plus 1 over 2 factorial, and then that is I h bar t over 2m second order derivative squared plus dot dot dot. So there's a third order term, a fourth order term, so forth, so on. We can now expand the initial wave function. And that would be 1 over pi to the 1/4 times 1 minus x squared over 2 plus x to the 4th over 8. And they are then higher order terms from there. And so what the book suggests in the problem is that you take these and then you basically distribute them. So you take the propagator, apply it to this wave function by taking 1 plus I h bar t over 2m second derivative plus 1 over 2 factorial I h bar t over 2m second derivative, that term squared, and then multiply it by 1 over pi to the 4th power 1 minus x squared over 2 plus x to the 4th over 8 plus dot dot dot, like so. So you can truncate it like the third or fourth order term. So basically now we're just going to multiply terms. So you would take the 1 times the terms in the wave function, and then you would take the derivative and apply it to the terms in the wave function. Take the next term, which would be the derivative to the 4th power, and then apply it to all of them. Group together all of the terms, and then you would arrive at your final time evolved wave function. Okay. So I'm going to stop here, and then in the next video I will continue this process.